Hi, welcome back. We're still talking about Coulomb's law and continuous distributions. In the last video, we considered an object that was kind of one-dimensional, like a rod or a wire. And in this video, we're going to consider something that's two-dimensional, like a plate or some sort of surface. All right, so let us get started. We're going to work through an example, and I have that example already ready to go. But for right now, I don't want to get to that just right now. So just ignore what I have there. Um, so again, I want to remind you that in the last video, we had something called the linear charge distribution or the linear charge density, right? Rho L, and this should not be confused with the rho of cylindrical coordinates. And the idea is that this rho L tells us how the charge is distributed along a line. The L stands for line. And we applied Coulomb's law to like a finely sliced piece of the line. And then we integrated Coulomb's law to figure out what the electric field was due to that rod or that wire. Now, we're going to suppose that the charge is distributed in a surface, and the charge is then a surface charge density, and so we're no longer going to look at rho L, but we're going to consider rho S. S stands for surface. And again, we're not going to confuse that with the rho in cylindrical coordinates. And you should be able to guess at this point that rho S has units of coulombs per square meter now. How is the charge, or how are the coulombs spread out over a surface? Coulombs per square meter. So if the charge density is uniformly distributed, then this rho S is a constant, and it does not depend on the location of the surface. And I want to give you an example there. Let's suppose we have some sort of sheet, maybe in the XY plane. Okay, so here's X coming out at you. Here's Y. And we'll say that the sheet is uniformly distributed with charge. These plus signs that I'm drawing represent the charge. So they're uniformly distributed, so they're evenly spaced. That means that if I consider maybe this point here, we'll call that point XY. All right, and if I take a piece of this thing with just a piece, so it's got a surface area, and that x changes by delta x, and that y changes by delta y, all right, then we would say something like, first of all, the change in surface is delta x, delta y, right? And the charge then on that surface, that piece of surface, we'll call that Q1, that would be rho S evaluated at that point xy times delta S. So why is that? Because rho S is in coulombs per square meter, multiplied by the area square meters, then we've got coulombs. Now if we take a piece of this area, maybe here, we'll call that xy now, and it's the same size, so it changes by delta x, delta y. So again, that thing has delta S, maybe call this, maybe this is delta S, yes, delta x times delta y. Now the charge there, delta Q2, is rho S evaluated at xy times delta S. It's the same. All this is to say that when we take a slice here and an equally sized slice here, because charge is uniformly distributed on the plate, then we get the same charge on those two surfaces. So let's contrast that with a plate like this. Here's X coming out at you. Here's Y. Here's our plate. And something that is not uniformly distributed, maybe the charge density increases around this corner right here, something like that. So this is an example of something that's not uniformly distributed. So in this case, you would need a function to model rho S. Rho s may be something that says that it increases as xy increases. So now if we take an area here, delta s, right, delta s equals delta x delta y, the charge on that plate would be rho s evaluated at xy, maybe here's point xy, times the surface area, delta s. But if we take that same slice, that same sized slice here, we would get delta q2, rho s evaluated at xy, maybe this is xy, times the same area, delta s. But even though it's the same area, what we find is that q2 is greater than delta q1, right? Because it's not uniformly distributed. All right, so we saw something very similar in the previous video. Hopefully that makes sense, and hopefully you have a good understanding now of this rho s. So now we're going to consider a following example, and again I want to say that this process is just as important as the result. Understanding the process means that you can find that result for different distributions and different examples. So here's the problem. Suppose that we have an infinite sheet of charge and it has a uniform charge density of rho s. Determine the electric field anywhere above or below the sheet. So whenever you see infinite sheet of charge, all that means is that the dimensions of the sheet are much larger than any other relevant dimensions. So the sheet here in my figure, I've got it oriented in the xy plane. So that would mean the dimensions, the xy dimension, are much larger than the z dimension. Maybe we're considering the electric field in the z dimension, and if that's the case, we can consider the sheet to be infinitely charged, or infinitely long, excuse me. All right, so I've drawn a diagram here, and again I said that the sheet is in the xy plane. And first, we really need to choose an appropriate coordinate system. Don't expect the figure to be provided for you. A sheet, the word sheet, implies a flat surface. So Cartesian or cylindrical would be okay. You would not want to use spherical coordinates here because there is no flat dimension in spherical coordinates. But we're going to choose cylindrical. Then what you need to do after you've chosen the coordinate system, you need to orient the axes and choose the origin to simplify the problem. By the way, we saw a similar process in the previous video. So we're going to place the sheet on the xy plane. You can think of it like a baking sheet just lying on a table. And it's infinite. So that means that rho, the rho dimension, the radial direction, extends from 0 to infinity. But it's infinite all around the xy plane, so that means that phi, the angle that this thing makes, right, the angle at any point, phi must extend from 0 to 2 pi. It must extend all the way around. So phi goes from 0 to 2 pi, with rho going from 0 to infinity. That's the entire xy plane. And the center of the sheet, we're going to say then, is at the z-axis. All right, I've got a small little chunk of my sheet, infinitesimally thin chunk, small chunk, ds. And I've got that represented here. We're going to consider the small little piece of our sheet located at rho prime phi prime 0 to be right there. I'm using the primes to represent the location of this infinitesimally small piece, and it has to be at 0, z equals 0, because we've oriented the sheet on the xy plane, so z equals 0 by definition. And then we're going to consider the electric field on the z-axis. On the z-axis, rho is equal to 0, but phi and z can be anything. And that's called, remember, our field point. So here's our kind of our differential point with the prime coordinates, and then our field point is the unprimed coordinates. I've also drawn the vector, right, the distance vector, the distance vector from the primed coordinates to the unprimed coordinates. So we're going to take that incremental change in the sheet, right, and consider its differential surface area. So this now we have to tie into what we said with our coordinate system videos. ds, well, what is changing? Rho changes, right? Rho goes from this point coming out at you. And phi also changes. There's a change in the angle. So what is rho s in that case? What is ds in that case? So that would be rho prime d rho prime, right? For the change in and we need a d phi prime as well. So the rho prime d phi prime is for the change in phi, and the d rho prime is for the change in rho. And because charge, we're considering the charge on this thing is a scalar, we're going to use ds instead of d vector s. So what I mean is that dq, the charge, the differential charge on this little piece is, remember, rho s, the charge density, times the area. So that is, again, rho s, rho prime, d rho prime, d phi prime, like that. Now let's talk about the distance vector r prime. So that goes from ds to the field point. We want to know what is the distance of any segment of our sheet to the field point. So the distance vector r prime, notice to get back to the z-axis we have to go backwards in rho. So we've got minus rho prime in the rho direction, and then we have to go, in my drawing, we have to go up z. But if z were negative, then this z would be negative, but we're still adding, we would be adding a negative. So we're still just going to say plus z az, right? So again, we go in, hence the negative, the rho direction by rho prime to get back to the z-axis, and then to get to our field point, we go up plus z, wherever that field point is on the z-axis, in the z direction. The magnitude of that distance vector then is what we call just r by itself without an arrow. That would be rho prime squared plus z squared to the 1/2 power. Right? Pythagorean theorem, square root of each component squared. Now we can consider the electric field just due to that small little segment. So that would be dE is equal to K times dQ over R squared times a unit vector in that direction. All right, so I have most of these things. K is a constant. dQ, we said, is this thing here. So that would be rho s, rho prime, d rho prime, d phi prime, over r squared, and then a unit vector in the r direction. So a unit vector in the r direction is r divided by its length, which is r, without the arrow. So that makes r cubed down here. So this dE, the differential electric field, is then K rho s rho prime d rho prime d phi prime times r, and we have r, that's negative rho prime a rho plus z az, all over rho prime squared plus z squared to the 3/2 power. So 1/2 comes from here, like the square root of the sum of the squares, and then the 3 it comes from this cube here, so we have to the 3/2 power. Now, imagine this figure, and imagine going into the page. There's an equal and opposite section of the sheet that will point at our field point that will cancel the row direction of the electric field. And so for any segment, actually, there's going to be an equal and opposite that cancels in the row direction. And so from symmetry, we've identified the symmetry. When we add or when we integrate around the sheet, around all the DS's, the components of E, the electric field, in the row direction will cancel. So all we need to do is calculate the Z component. That's nice. So we'll say EZ, so the Z component. The phis are going from 0 to 2 pi as we discussed. The rows are going from 0 to infinity as we discussed. Then we have K, rho S, rho prime, Z, that's from this guy, over rho prime squared plus Z squared to the 3/2 d rho prime d phi prime, like that. And so now it becomes a math problem, and we have to solve this integral. I guess before that we can take out some constants. Let's do that to simplify our lives. K is a constant, rho S is a constant, and Z, as far as rho and phi are concerned, Z is a constant as well. So we can take all of those guys out. And you might ask, why is rho S a constant? Because this is uniform charge density. Okay, so I'm taking those guys out, so I'm left with rho prime over rho prime squared plus Z squared all to the 3/2 d rho d phi, like that. So we have to figure out how are we going to integrate this guy. And in the previous video we used trigonometric substitution. For this one we can handle with U substitution if we let U be rho prime squared plus Z squared. So in that case du is equal to 2 rho prime d rho prime, like that. Alright, so this should be no problem. This is the first few weeks of Calc 1, or Calc 2, I guess, integration. So we've got K rho S Z. Rho prime goes from 0 to 2 pi. And U now, well, when rho prime is 0, U is Z squared. And when rho prime is infinity, U is also infinity. So my bounds for U are going to go from Z squared to infinity. And then what I have is one half U to the minus 3/2 power du d phi prime. So let us understand that a bit. If I make the substitution, I put U in for the denominator, so I have U to the 3/2 in the denominator, so that's U to the minus 3/2. Where'd the 1/2 come from? Well, when I differentiate this substitution, I get du equals 2 rho prime d rho prime. But so I need to substitute in for rho prime d rho prime. I need to get rid of the rho primes. So I divide by 2 and I see that 1/2 du is rho prime d rho prime. That's where the 1/2 du comes from. All right. So I can integrate that guy and I get negative k rho s z when I integrate with respect to u. So this is still phi goes from 0 to 2 pi. And then I need to plug in u goes from z squared to infinity d rho prime, like that. And when I do that, I get k rho s z. Phi goes from 0 to 2 pi of 1 over z d rho prime. So that's really nice. So when I plug in infinity into u, I get 1 over infinity is 0. When I plug in z squared, I get 1 over z, and then so that's 0 minus 1 over z, and so that minus cancels, and I get positive 1 over z there. There's no phi here, so this is a constant as far as phi is concerned. Let me erase a little bit. So as far as phi is concerned, this is constant. So that means that I can just tack on a 2 pi. So I get the electric field in the z direction is just 2 pi times k rho s. Wow, that simplified very nicely. And let me remind you that k is 1 over 4 pi epsilon 0, where epsilon 0 is the permittivity of free space. So I can alternatively write this to get rid of the pi's in very, very simple notation like that. And then let's bring back the vector notation. Remember, this is the z component, so now I can just write this. This is in the z direction. That's the answer. Very nice. Now, what's so special about the z direction? Right, our answer is in the z direction. Well, we chose to orient the sheet in the xy plane, so the z direction is just normal to the plate. So really this, to have an answer that is independent of how we chose to orient it, we should say an, where n is a normal vector to the plate or to the sheet. Now, I want to point out a couple things with this answer. First of all, notice, maybe surprisingly, that the answer is independent of z. Z is the height at which we're considering the electric field. So we can go as high as we want to, as far away from the sheet as we want to, and the electric field intensity still remains the same. That's surprising, but that's actually a property of the fact that the sheet is infinite. Also, notice that the electric field is proportional to the surface charge density. That makes sense. If you have more charge on your sheet, right, per area, then the electric field is going to increase as well. So this is telling us that it increases proportionally. If you double the amount of charge on your sheet per area, then the electric field doubles, and so forth. Further, this result holds for any row, not just at the center, right? Initially we chose rho equals 0, so that we're at the center of the plate. This thing holds for all rho because the sheet is infinite, so it has no center. And so that is our final result. Pretty awesome. Now, if you don't think that that's awesome, I don't know. I don't know. I don't want to go to any parties with you, because this is what I talk about at parties that I go to. This is what other people talk about at parties that I go to. So we looked at now linear charge distributions, and we looked at surface charge densities or distributions, and now we're going to look at volume densities or volume charge distributions. So I'll see you in the next video.